This next segment has to do with what we call units, and I know most of you are somewhat familiar with units, but units is really how we know what a number means. Earlier, actually, I said something about a temperature, I believe, and I didn't say whether or not it's Fahrenheit or Celsius. If there's no context, right, you don't know what that means. So, like, for example, it's 40 degrees outside. Well, in the U.S., in Fahrenheit, that means it's cold. And a lot of European countries, 40 degrees is in Celsius, and it's really hot, right? In Fahrenheit terms, it's over 100 degrees. Okay, so having said that, units are important for helping us understand what a number means, and also um, in order to compare numbers to other numbers, they need to have the same unit. We need to be talking about apples and apples. And so unit conversion is also something that we do to help us understand what numbers will mean or mean to us. Okay, so let's talk a little bit about units. So the system that we use is primarily known as the metric system. Um, it's related to something called the SI system, but to metricize something simply means to convert it into something that's evenly metered or has some logical way of being subdivided. Uh, Temperature is not one of those things. The temperature of freezing water in the Fahrenheit system is 32 degrees, and the boiling point is 212 degrees. It's not clear how that breaks down. The metric system was invented as an idea from a guy named Anton Lavoisier, and Lavoisier actually had a couple of firsts. He was the first one to make a list of elements. He discovered the law of conservation of mass, that mass is always conserved during any chemical process. And he also discovered oxygen and hydrogen, but the metric system is something he's not really that well known for. Maybe because he had his head cut off because he was tax collector in the French Revolution, or maybe because not all of his ideas were that widely accepted. This, what's shown on the right over here, is known as a metric clock. It was one of his invention, and he split the day up. Instead of having 24 hours in a day, he had 10 hours in a day, and there were 10 days in a week. So to make things better, he had 3 weeks in a month. That comes out to 30, and there were 12 months. That comes out to 360. But there's 365 days in a year. So what did he do? He just made 5 days of holidays and stuck them at the end of the calendar, and they weren't numbered. It was kind of a weird idea, right? Because you have a year where you have days that have no days. Was just kind of not right. Anyways, that was not well accepted. But part of that ends up, in the metric system at least, ends up being known as the System International Units. It's a system of international units. That's French, but anyways. And there are 7 base units, and then it turns out every other unit that we know. You notice there's not a joule up here, and I talked about a joule earlier. Every other unit that we know is derived from these 7 base units. For example, when we talked about a joule, that was a kilogram meter. I got to move these controls. Sorry. That was a kilogram meter per second squared, meter squared per second squared. So that's actually a joule. Hang on. A joule is equal to a kilogram meters squared per second squared. You'll notice that that's actually made up of 3 different SI units: the kilogram, the meter, and the second. Okay, so K is the unit for temperature. Not to be confused with this K, okay? That's Kelvin. There's no degree symbol, so we say it's, for example, 300 Kelvin. We don't say degrees Kelvin typically. Although, if you say it, most people don't really care. And then in the metric system, that would be degrees Celsius. Seconds are the same in the SI system and the metric system. Meters are the same in the SI system and the metric system. There's a difference in kilograms and grams for SI. Like I said, in chemistry, we typically use the metric system, so we measure stuff in grams. Candela, that's what that CD stands for, candela, spelled like candle, but with an L and an A at the end, is the same unit, and that's a luminous intensity. It's how bright something is. It's a measure of brightness. Originally, candles were candles, right? That's how bright we measure. So it's the number of candles something was, a standard candle. Mole is the quantity of substance, and A is electric current. That's in amps. And those units are the same. So you notice the only place that they're different is in temperature and in mass. Now, having said that, these base units for temperature, time, mass, length, mass, brightness, we'll call it that, simplifying it a little bit, quantity of material, quantity of substance, didn't leave enough room, and electric current. Right. In addition to these 7 sort of classifications of units, and not barring the compounded units like a joule that's comprised of multiple SI units or metric units, we have something called prefixes. Now, prefixes are what we use to express really large and small numbers. And this is roughly the list you have to have memorized. I think it's actually the list. Atto may not be on your list actually to memorize, but and you know where to find that from watching the introductory videos. But the prefixes are used to represent different powers of 10. So basically a replacement for scientific or exponential notation to simplify things. So giga means 10 to the 9th. So let's say I have 9 gigawatts, like that, right? That's actually 9 times 10 to the 9 watts. This, right, is the replacement of that. So that's the way we use these prefixes. So if we want to, those are for large numbers. So if we want to express small numbers, then we use prefixes that are femto. So if you have 1.5 femtoamps, that's equal to 1.5 times 10 to the minus 15 amps, like that. And this represents the femto right here. So the next thing to talk about is converting units, and we use a system called dimensional analysis, where you take all your calculations and you string them together and do them in one long calculation. And the reason, it seems weird to do that, but the reason we do that, it's easy to check your work, and there are fewer steps where you actually have to write stuff down and potential places for you to make mistakes. And so it's nice to do it this way, and it's the way that I require you to do your problems in this class. So let's do a dimensional analysis problem, and we're going to do prefixes first, and then we'll talk about converting between English and metric and stuff like that. But let's talk about a prefix conversion. So I have this 20,150,000 watts, and I want to convert that to megawatts because that would just seem to be a lot more appropriate. So the way you do it is this. You know that this is your map. This is what you want to do, and it's a prefix conversion. So you need to find the relationship between watts and megawatts. And the way you write that is this. You would say, you can say 1 times if you want. 1 times 10 to the 6 watts is equal to 1 megawatt. And the thing to remember is this number and the prefix are always on opposite sides. This is the relationship between watts and megawatts. Now, the way you solve the problem is you start with what I usually tell students: write the unit you're looking for here on the left side and say that's equal to, okay? And you start with a given number and its unit, and then you write the conversion factor, that's this, in this way. 1 times 10 to the 6 watts, right? and then on top you write the other half of the equation, 1 megawatt, like this. Now the reason we do that is we know that these two are equivalent, okay? And by placing one over the other, what we're doing is essentially multiplying these. This is a quantity of 1. We're multiplying by 1 in a sense to replace the units. So what we're going to do next is cancel out the units we no longer need. We'll do that by doing this. And then you're left with the unit you're looking for that matches this unit over here. And that's kind of why I have students do that. Now, in these one-step conversions, it's not that important that you write it out like that, but it's a good habit to get yourself into. If you can cancel out the units and you can end up with the units you want, then that's all you need to do. Okay, and I'll show you how to use that idea in longer problems when we're about to do a couple of longer ones, but just to get the idea of dimensional analysis. So now what I'm going to do is I'm going to go ahead and do the math. This is actually going to come out to 20.15, and then everything else will divide away, megawatts, like that. Now that's just a much nicer way to express that number rather than having all those zeros. So this is one of the real common uses of prefixes, to get rid of a lot of the scientific notation, which is really hard to look at, or get rid of a lot of the placeholder zeros that are really hard to look at. Okay. So the idea is this: you have the old unit, and you're going to multiply it times the ratio of a factor of a over b. In this case, a over b is 1 over 1 times 10 to the sixth, right? And you're going to set this up so the one old unit is in the numerator, because you can think of it like that, right, over 1. And then the other one is in the denominator. And then those units will cancel out, and all you're left with in your answer is this new unit, or the unit that you're looking for. Okay, let's do another one. Now what I want to do is I want to go between micrometers and centimeters. So this is what I'd like you to do, at least initially. You're going to write it like this: micrometers, and you go back here, right? And micro means 1 times 10 to the minus sixth. So I can relate micrometers to meters. That's 1 times 10 to the minus 6 is equal to micro. That's a Greek lowercase m. And then I can go from meters to centimeters, because I know a centi, right, is equal to 1 times 10 to the minus 2. Now, maybe you don't know that, but you're going to have to know that. There's a quiz coming up. Centi is 1 times 10 to the minus 2, and you might know that because there's 100 pennies in a dollar, and that's what we call penny cents, right? It's 1/100th of a dollar. And 1/100th is 10 to the minus 2. So what you do next is, this is your problem map. It gives you the idea about how you're going to do the calculations. And I know I can get to the answer with this because I have micro, and then I have meter, and then I have centimeter. So I have a continuous string of conversion factors to get to the answer. So now what I'm going to do is write that I want centimeters, right? And I'm going to write 350 micrometers. By the way, this is the answer, so let's see what we get here. Make sure that kind of works. All right, 350 micrometers, and then I'm going to convert it to centimeters. So the first, and by the way, you can set up, this is something called railroad tracks. Students will do this a lot, and they like it. I think it's nice because it keeps things separated and clean. Then I'm going to say at the bottom I want micrometer, right? But that means at the top I have 1 times 10 to the minus 6 meters. Now, you might get tired of writing the 1 times 10 to the minus 6. That's actually implied when you just write it like that. But I'll go ahead and do it like this for a while, because people hate just seeing a 10 to the power there. And then I want to do the next conversion. So what's this going to do is this process up to here has gotten me to meters. And now I need to go from meters to centimeters, right? So I want to get rid of the unit meter. So I'm going to have meter at the bottom, and I'm going to have centimeter at the top, like this. And then a centimeter, right, is 1 times 10 to the minus 2 meters, like that. Remember, the prefix and the number are always opposite of each other in terms of numerator, denominator. And then what will happen is meters will cancel out and have units of centimeters. And so when you carry the math out on this, this comes out to be 0.035 centimeters. And if you're not sure how to do that, I will use this calculator only once here. Let's see if I can pop it up. Let's see here. There we go. So there's the calculator. It's a really horrible calculator to use, and then I'll go ahead, but I'll do it once so you can see how you enter this in your calculator. So you're going to type in 350, right? And then you're going to multiply time. You already worked out that the units come out to centimeters, so you don't have to worry about units when you do the calculation. 1, so times, sorry. 1, scientific notation is that key, times 10 to the negative 6. So you're going to enter it like this, negative 6. So you actually don't have to type in the 10. And this is true for your calculator too. I want you to use on your calculator, there's an EE button or an E button. I want you to use that. It's not this lowercase e. That's actually a natural anti-log function, and I don't want you using that one. But you use this button. So what I've done is said 350 times 1e minus 6, so that replaces this, and then I'm going to divide it by 1e minus 2, so on the Microsoft calculator you have to do the number and then change the sign. And I'll hit enter, and then I get that answer, which I already told you is the answer for the problem. Is this one up here I scratched out earlier. Is going to be 0.035 centimeters. Okay, so that's the idea of using unit conversion for prefixes, but there's a lot of other times when we would use unit conversions, and one of the common ones is what we call English to metric conversion. The English system is what we use here in the United States. It's inches and feet and miles and things like that. Now, so let's do a calculation. We're going to say how many centimeters are in 1.75 miles. And what you need to do is you need to look up unit conversion factors to do these problems. Now in the worksheet that we're doing that's associated with this, I gave you a list of conversion factors. Your book has a simplified list of conversion factors in the chapter, and it also has a much larger one, I think, in the right at the end of the book, on the inside cover. Okay, but where'd it go? Oh, my slide disappeared. Well, I'll have to get it back. Hang on. Yeah, I had a computer crash earlier, and then some of my slides apparently disappeared because I'd been editing the file. But anyways, this is a table from Chapter 1, and it lists some common units and their equivalents, so conversion factors. Here's what I want to say about this. It's really helpful when you know the kind of unit that you're talking about. So remember we classified as like meters, second, kilograms. Those are different kinds. Meters is length, seconds time, that kind of thing. So these are common conversion factors, and this is the way you usually find them. They're usually separated out by the type of dimension that we're talking about. The unit is known as the dimension, type of unit that we're talking about. So if you go back to this problem, you say 1.75 miles in centimeters, so that's a length, right? So you know you would find that in this column. So what we need to do is convert miles to centimeters. Now let's see, what do we have up here for a mile? I have 0.6214 miles is a kilometer. Okay, so I'm going to go back up to here. I'm going to write that down. 6.12, let me double check that real quick. 0.6214. I don't know where I got this. 0.6214 kilometers equals 1 mile. And then we're going to do a little thinking on this, right? If I want to know centimeters, then I know 1 kilometer, right, is equal to 10 to the third meters. And then I also know that 1 centimeter is 10 to the minus 2 meters. So you notice what I did is I have a clear path from, I'm going to change color pens for this, I think. Oh gosh, didn't want to do that. color pens for this. I'm going to do this in green. I have a clear path between miles and centimeters. And what I mean by that is I have a mile here, and that takes me to the kilometer, right? The kilometer takes me to the meter, and then the meter takes me to the centimeter. And I can string together conversion factors, and it doesn't matter like which conversion factors you use really, as long as they can get you there, okay? So it's like taking a drive out in the country to, let's say, go visit, go visit my mom, for example. There's numerous ways I can go out to drive to my mom's house, depending on like what I need to do on the way there, whether I want to take the scenic route or the fastest route, and those kinds of things. And it turns out unit conversion is pretty much the same thing. Sometimes there are more efficient ways, but sometimes there's just ways that are easier than the most efficient way because you know the conversion factors. So having said that, I'm going to start with what am I looking for, right? So I'm looking for centimeters, so I'll start with that on the left-hand side. And then I'm going to say the given number is 1.75 miles. And again, I'm going to set up my conversion so that I'm canceling units the whole way. And I'm going to do something here so you can see how this works. I know I need that many conversions, and I'll show you how I know that in a second, right? I know that there are 0.6214 kilometers in 1 mile. And so after this step, I will cancel out miles and I'm left with kilometers. So I put kilometer at the bottom over here because I want these two to be canceling out with each other. And then I'm going to have at the top is 10 to the third meters. Now I'm going to not use the 1 times 10 to. Hopefully you get the idea now that you can do that, but it takes up too much space when I do these. And so I'm going to be, after I cancel these units out, and I'll do that here in a second, that I'll be left with meters. And so I know that 1 centimeter, that's what I want on top, and I'm going to want to cancel unit is 10 to the minus 2 meters, okay? So in my unit canceling, I'm going to cancel like this. And then all the math is all that's left because I know I'm left with units that I'm looking for. So now I can take my calculator and plug all those things in, and I lied. I guess I'll go ahead and use that calculator one more time as much as I hate it. I can just run the math. It's 1.75 times 0.6214 times, and then you have to do the 1E3 and then divided by, make sure I got everything in right, yeah, 1E2 change sign like that, and that's going to come out to this huge number, but it makes sense, 108,745. Because really a centimeter is pretty small, right? And a mile's pretty big, and so you'd expect there to be a lot of centimeters within a mile. Okay, let's do another one. Now this is kind of a different one. One of the things a lot of us have been doing with coronavirus is cooking, and then we also haven't been moving, so the other side thing we've been doing is gaining weight. But having said that, right, the recipe calls for 345 grams of butter. That's actually a croissant recipe. How many tablespoons of butter is that? Because, like, in the in England, they weigh out a lot of foods. And in a lot of recipes now, people are, everybody has these kitchen balances or scales. But a lot of times, if you don't have one of those, and it says 345 grams of butter, how do you know how much that is in tablespoons? Because like a tablespoon is cut into 8 sticks. Or a butter stick, a standard stick is cut up into 8 different tablespoons. Anyways, so let me read this question to you. It says, your recipe calls for 345 grams of butter. How many tablespoons of butter is that? And then it says there are 8 tablespoons and a quarter pound of butter. That's 1 stick, okay? So let's go back, and we need a mass conversion right? And what mass conversion do I need? Well, I know that there are 8 tablespoons in a quarter pound of butter, and then I need 345 grams. And you'll notice these are the mass units, and this is why this is important. So I need the unit conversion between pounds and grams. I'll go back, and then I'll go, okay, here's pounds, because this is the mass column. There's pounds and there's grams. So 453.59. So remember that. There's 453.59 grams, and that's equal to 1 pound. It doesn't matter if it's a pound of feathers or a pound of butter, right? So a pound is a pound. So I can go, this is my thought process, okay? I have grams, and then I can go to pounds. And then you notice I could go to stick, because that's one stick. One stick is 8 tablespoons, but 1/4 pound is also a stick. But then I say, oh, wait, 8 tablespoons is a 1/4 pound, so I say, oh, then I can go to tablespoons. Okay, so now what, right? I have all the conversion factors I need. The other conversion factor is 8 tablespoons is equal to 0.25 pounds. And that is what we call an equivalency created from like a sentence. Like if you're told that that's what that is. Some of you already knew that, of course, because you've been cooking like we have. But anyways, let's go ahead and say I'm looking for tablespoons. And I'm going to start with 0.25. Oh, sorry. I'm going to start with the given number, 345 grams of butter. Right? And, oh, I forgot to tell you why I knew exactly how many of these to put in there. And then I know that there are 453.59 grams. So where does that go, right? I need to cancel grams, so that's going to go down here. And then it's going to be, I can't actually fit the number in here, 453.59, because I wasn't thinking far enough ahead, and that's 1 pound. And then I know for 1 pound, I have 8 tablespoons. And then I can do my calculation. And again, I didn't think I was going to use this calculator, but I like you seeing the calculation. And so it's going to be 345, right, divided by, oh, I'll do it with the mouse so you can see it, 453.59, and then times 8. And that comes out to almost exactly 6 tablespoons of butter, right? 6.1 roughly. So we'll go ahead and write 6.1 tablespoons. All right. So again, that's the idea of unit conversions. What you want to do is you want to look at the unit you're given and look at the unit you want to find, right? And then find all the conversion factors before you get started that connect you. And you might find a different way. You might add an extra calculation, or you might find a more efficient one and get rid of a calculation. But here's the thing I want to make sure you do. Don't Google all the answers. The reason I say that is because sometimes you're not going to be able to find the answer by Googling it. If it's a question like this, you most likely won't find it, okay? Where a conversion is given in the sentence form that relates, for example, tablespoons. Well, this one's pretty common, so you might find it tablespoons to something else, okay? Or there's another one, right? 1 kilogram is equivalent to 2.205 pounds. What is the mass of a 10-pound block of ice in grams? So let's think about this problem. In fact, what I'll do is I'll let you work this problem out, and I'll pause the video, and when we start it again, you'll see it all worked out, and I'll just talk us through it. But before I do that, I just realized I forgot to talk about this again. You notice I set this up before I actually did the calculation. So how did I know that's how many things I was going to need? I knew that because every line, right, relates to one conversion. So for every, this is one of the reasons why I like looking up the conversion factors beforehand. I know exactly how much space I need to do the calculation. Same thing was true on this problem. There's 3 conversion factors, so there's 3 lines and there's 4 groups of numbers, because you start with the number that's given, and then every line represents one of these conversions. Okay. So go ahead and do this problem. You'll know if you did it right because that's the answer at the bottom right. Okay, I'll pause it and I'll fill. Okay, so here is the problem all worked out. I found the conversion factors. Oh, I forgot to write my plan. Sorry. I'm going to go from pounds to kilograms, right, to grams. That's kind of the logical progression. I found a conversion. I'm given a conversion between 1 kilogram is 2.205 pounds. I'm given that one. And by the way, on test problems, when you're given a conversion factor, use the given conversion factor, because that's how you'll get to the right answer. Even if we fudge it and make it a little different or round it, you got to make sure you use the one that's given. That's how you get the right answer. Okay, anyway, side note. The other conversion is just a prefix conversion. There's 10 to the third grams is a kilogram, right? So 1 kilogram, that is this down here, right, is 10 to the third grams, like it is over here. Because kilo is 10 to the third. Again, prefix, number, opposite sides of the equation. And then that allows me to write this. So I strung it out. I did it so that my pounds would cancel. It would be nice if pounds could cancel. And then kilograms cancel, and I'm left with grams. And so I do 4,535 grams. We haven't done sig figs yet, but you'd round that to 3 sig figs later. We'll come back and round some of these problems later. All right, so another type of unit are area and volume units. These are derived units, just like density is a derived unit. And they're a little bit tricky to handle. What ends up happening is in the unit itself, right, it becomes cubed, for example. So like a milliliter turns out to be, and this is one of those relationships you need to know, 1 centimeter cubed, or 1 cc, is equal to 1 milliliter. I won't talk about the origins of it really, but a 10 by 10 by 10 centimeter cube has 1,000 cubes in it, and that's the definition of a liter. It turns out it's 10 centimeter by 10 centimeter by 10 centimeter by 10 centimeter by 10 centimeter cube is what defines a liter, and so there's 1,000 cubic centimeters in a liter. All right. So how do you deal with these in unit conversions? Well, if the unit conversion was centimeters to inches, then what you would do is just use this conversion, right? Because this would cancel the centimeters and leave with the inches. But if it's squared, then you have to cancel this twice because there's 2 of them in there. So you end up having to square the conversion factor. So one of the things that gets people all the time is they'll square the inches and the centimeters, but they don't square this number because they forget how it distributes within the whole parenthesis. So British A4 paper, right, has an area of 623.7 centimeters squared. Is that bigger or smaller? How does it compare to U.S. letter paper? And anybody who's used it kind of knows, but I'll save that for later. But how does it compare to U.S. letter paper? So what we want to do is take 623.7 centimeters and convert it into inches squared. And then we want to calculate the inches squared here and then compare the two. Okay. Well, and actually, we could go the other way too. You could go from 8.5 inches and convert that to centimeters, and 11 inches and convert that to centimeters, and multiply that out as well. So there's a couple of ways to do this, but the way I intended to do it was to convert this number here. So I'm looking for inches squared, right? And so I'm going to go 623.7 centimeters squared. I have one conversion that I'm going to do, and that's going to be 1 inch over 2.54 centimeters, right? And then I'm going to square this whole thing. So this will cancel, because that's squared and this will be squared. But then I basically have to divide this number by 2.54 centimeters. I got to take the 2.54, I got to square it. So again, getting this calculator that I really don't like. I'm going to go 6. I can't type to save my life. 623.7, and I'm going to divide it by 2.54 squared. And we're going to hit equals, and that's 96.67 inches squared. So how big is a standard piece of U.S. letter paper? So all right, letter paper would be in inches squared would be 8.5 inches times 11.0 inches. And again, back to my favorite calculator. Yeah, I didn't say that ever. 8.5 times 11 and 93.5. Come on, pen. Inches squared like that, because when you're multiplying these together, right, you need to square them. So actually, U.S. letter and standard A10, right? A10 papers, A4 paper is actually larger. All right, and actually, I worked it out down here too. I do that with a lot of my slides, by the way. If I forget to say an answer, skip a slide, and you want to do it, the answers are typically on the slide somewhere. All right. Next thing, density.